we will explain subgroup. Okay, so as you know, what is group? So first we have group, any set. This is a set. So any set is said to be group if it satisfying four properties with given operation. Suppose this is a non-empty set G. So this set G with given binary operation G star is called group if it satisfying four properties. Means this has closure law, this has associative, okay, this has identity, and each elements have inverse. Okay, means this is a non-empty set. This non-empty set with given operation satisfying four properties. First is closure law, second is associative law, third is identity law, and fourth is inverse law. Then we say that this G with given operation is called group. Okay, so as you know, the concept of set and subset. So what is set? So set collection of well-defined things is called set. Suppose A is equal to 1, 2, 3, 4. Okay, this is non-empty set. And if we take some elements from A, suppose B is equal to 1, 2. Okay, means this is A, this is 1, 2, 3, 4. And we take B, means this is B. Okay, so here you are very familiar to A and B, means B is a subset of A. Okay, so in the same fashion here G is a group. So first G is a non-empty set. Okay, G is a non-empty set. So we will take a subset of G which is non-empty. Okay, which will be similarly if G is a group and any subset of G which is non-empty. Suppose this is a subset of G, this is H. Okay, this is H. And this property contains closure, associative, identity, and inverse. Then we say that this is a subgroup of G. So what is the definition of subgroup? Means if G is a group and H is a non-empty subset of G, then if H is itself a group, then we say that H is subgroup of G. Okay, the concept of subgroup is very easy. It is itself a group. It means H satisfying closure property, associative property, identity property, and inverse property. So what is the definition? Definition is very easy. Subgroup. So let G with this operation star be a group, and H is a non-empty subset of G. Okay, H is a non-empty subset of G, then H is called subgroup of G if H star is itself a group. Okay, so this is the definition. Means H is subset as well as satisfying four properties. Then H is called subgroup. Okay, so there are two types of subgroup mainly. Means one is improper and other is proper. Okay, so this is important, means first is improper subgroup, improper, and second is proper. Okay, so what is improper? So as we know, in a group, smallest group means if identity element with respect to operation is always a group. So identity element, if set contain only identity element, then identity element with operation, this is a group, means this is every set is a subset of itself. So similarly every group is subgroup of itself. So this is called improper or trivial subgroup. Okay, and other than this is called proper subgroup. Okay, all the subgroups of G other than improper subgroup is called trivial subgroup, is called proper subgroup. Okay, means if suppose set of integers with respect to plus is a group, okay, and if we take set of even integers with respect to addition, this is also group. So this is called subgroup of this. Okay, means set of integers with respect to addition is a group, and set of even integers with respect to addition also a group. So this is called subgroup of I plus. So this is called proper subgroup. So there are two types of subgroups, one is improper and second is proper. So we have identity element, a set contain only identity element with respect to operation is always a group, and this is smallest group. So this group is called improper subgroup. Okay, so this is the definition of proper and improper subgroup. One thing is important that you can ask if G is a group, means G have some elements, okay, with identity element. So this is a group, and any subset, this is subset of G, means this is H. But this H does not satisfying four properties. It means H is not a group itself. So if H is any subset of G, then in this case H is called complex. Okay, complex means any subset of G, is called complex. So what is the difference between subgroup and complex? So in case of subgroup, any subset H of G is called subgroup if H is itself a group, means H satisfying four property. But if H is only subset, okay, then this is called complex. This is the basic difference between complex and subgroup. Okay, so now I am going to some examples of subgroup. So let us suppose set of integers. Set of integers means -3, -2, -1, 0, 1, 2 up to so on. Okay, so we have this I with respect to addition satisfying four properties, means this is closed. For any two elements we add, then again in I. Okay, this is closed, means closure law satisfied. Second is associative. Associative means for any three elements of I, A plus B plus C equal to A plus B plus C. Okay. Third is identity law. So what is identity law? Identity means first you see what is the operation. So this is operation is addition. So here 0 is identity with respect to addition. So here 0 is present. Okay. So this is identity exists. Now what is fourth property is inverse. So what is inverse? Inverse is nothing but each element of I has its inverse, means 1, so minus 1, 2, so minus 2, and similarly if minus 2, so 2. So each element of I has its inverse. So since set of integers satisfying all four properties, therefore I plus is a group. And similarly, if we take subset of I means set of even integer. Okay, set of even integer means this is only we take 0, 2, 4 up to so on, means plus minus 2, plus minus 4 up to so on. Then first we check E plus satisfying four properties or not. So here it is easy to see. First is closure. So you take for any two even integer. So by adding we get again even integer, means closure law satisfied. Okay. Second, associative. So we have in case of addition associative law always satisfied. Okay. Now third is identity. So you check in the given set, since in addition 0 is an identity element, so here 0 is present. Okay, so identity element exists. Now inverse law. So what is inverse? Each element of E has its inverse, means inverse 2. If you take 2 belongs to even integer, so what is the inverse with respect to addition? Minus 2. So this is also in this set. If you take minus 4, so plus 4, it means all elements has its inverse. Therefore, set of even integer is itself a group. Since E is subset of I, therefore set of even integer with respect to addition is a subgroup of set of integers. Okay, therefore we say that set of even integer with respect to addition is a subgroup of set of integers with respect to addition. Okay, now this is another example, means if you take set of odd integers means 0 plus minus 1 plus minus 3 plus minus 5. So first you check set of odd integers with respect to addition is a group or not. Okay, this is a group or not. So first we check. So here first property is closure. What is closure? You take for any two elements of this set. Suppose 1 belongs to O, set of odd integers, and 3 belongs to set of odd integers. So here addition is operation. So 1 plus 3 is equal to 4. So 4 does not belong to set of odd integers. Okay, 4 does not belong to set of odd integers. Therefore closure property does not satisfy. It means this is not a group. Since set of odd integers is a subset of set of integers, but set of integers is a group with respect to addition, and set of odd integers is not a group itself. Okay, therefore set of odd integers is not a subgroup of I. Okay, so this is very good example which is not a subgroup. Means first you check given set is a group or not. So since set of odd integers does not satisfying closure property. Okay, not satisfying closure property. Also, you can tell that this is satisfied associative, yes. Identity, yes, because with respect to addition, 0 is here. Also, inverse exists, means set of odd integers with respect to addition satisfying three conditions: associative, identity, inverse. But this not satisfied closure. So this is not a group with respect to addition. It means set of odd integers is not a subgroup of set of integers. It is clear? So this is very nice example of subgroup as well as not subgroup. Okay, now some more examples, very important examples on subgroup. Now some important properties of subgroups. Okay, so this is the first theorem. Let G be a group and H is a non-empty subset of G, then H is subgroup of G if and only if two conditions satisfied. Okay, so proof is very easy. So as we know, in a definition of subgroup, we have if this is a group. Okay, this is a group. It means G satisfying four property, means first is closure, associative, identity, and inverse. Okay, this is the basic definition of group. And if H is a subset of G, then H also satisfying four conditions, then we say H is a subgroup. Okay, now this is the first property, means if G is a group and H has only two property, means closure and inverse property, means this only two properties, this is closure and this is inverse axiom, then we have to show this is also a group. Okay, so very interesting that properties of subgroup. So there are two parts. First part is if we take G is a group and H is a non-empty set, then we have to show two conditions satisfied. And converse part, if H is a non-empty set and two conditions satisfied, then we have to show H is subgroup of G. Okay, now first part. First part, let G be a group and H satisfying H first part is that let G be a group and H is a subgroup of G, then we have to show that given conditions satisfied. Okay, means there are two parts. Means first part is that if H is a subgroup of G, then two conditions satisfied. Converse part, if H is a non-empty subset of G and satisfying two conditions, then we have to show H is a subgroup. So first part, suppose H is a subgroup, then we need to show these conditions satisfied. Okay, so as you know, it is very easy because H is a subgroup, then by definition H satisfying four conditions. Okay, so here H has four conditions, we need only two. So by closure law this satisfied and by inverse law this satisfied, so only we need to write. Okay, so here we have written let G be a group and H is subgroup of G, then we have to show given conditions satisfied. Okay, so since H is a subgroup, then since H is a subgroup, then by closure law, A B belong to H for every A B in H. Okay, means condition first satisfied. Also, since H is subgroup, therefore by inverse law, A inverse belong to H for every A in H. Okay, so first part established. Now converse part means, so what is converse part? Converse part is that let H is a non-empty subset of G and given condition satisfied, then we have to show that H is a subgroup of G. Okay, so now this is very interesting. It means converse part. What is converse part? Converse part is that if H is a non-empty subset of G and it's satisfying two conditions, means A belong to H, B belong to H, A B belong to H, and second. Okay, so we need four conditions. So two conditions already given. Only we need to satisfy two more. Okay, so first A B belong to H for every A and V in H, means this is closure law, satisfying always because by given condition first. Okay, now second is associative. So since every element of H also elements of G, because H is subset of G. Okay, so since G is group, it means all elements of G are associative. Therefore, all elements of H are also associative. It means this condition is satisfied very easily. Only we will write, since H is a subset of G, therefore associative property satisfied. Okay, now third, identity. So since closure satisfied, so we put given condition B is equal to A inverse by condition second. What is the condition second? For every A belong to H, A inverse belong to H. Okay, so now putting in condition first, A inverse belong to H. So A inverse means E belong to H. So identity axiom satisfied. Now fourth is inverse axiom. So inverse axiom is given by condition second. Okay, so therefore yes, satisfying four properties. It means what is converse part? Converse part is that if H is a non-empty subset of G and H satisfying only two property, means closure and inverse, then we have to show it's satisfying four properties. Okay, so very easy. We need to show H have four property. So two has given already. So we need only two more, means identity and associative. So by associative law, since H is a subset of G, it means all the elements of H are in G, and since G is associative, It means all the elements of G satisfying associative law. Therefore, all the elements of H also satisfying associative law. So third condition satisfied. Now for identity element, we will use given two conditions. Okay, here by second condition means for every A belong to H, A inverse belong to H. So putting in given condition first, B is equal to A inverse. So A inverse is equal to E belong to H. Identity axiom satisfied. Therefore, converse part satisfied and is proved. Now, this is very important theorem in subgroup. Okay, so what is the theorem? Theorem is that let G be a group. Let G be a group. And H is a non-empty subset of G. Then H is subgroup of G if and only if AB inverse belong to H. Okay, it means if H has only one property, for any two element A and B belong to H, AB inverse belong to H, then H is a subgroup. This is very useful in whole subgroup as well as group. Okay, as we know, we have discussed about subgroup. What is subgroup? Let G be a group. H is a non-empty subset of G. Then H is a subgroup if H is itself a group. Next we define and prove the theorem, means if H has only two property, then this is a subgroup. In this theorem, we will prove if H has only one property, then H is a subgroup. So this is very useful as well as very interesting. Okay, as we know, this is group. So group has how many property? 4. Closure, associative, identity, and inverse. Okay, as we know, if H is a subset of G, so by the definition H has also 4 properties. Okay, now we have proved recently if H has only 2 property, then also a H is subgroup. In present theorem, I want to show if H has only one condition, this, then H is a subgroup. Okay, so now first part. So first we will write common thing, proof of the theorem. Let G be a group and H is a non-empty subset of the G. This is the common for both the parts. First we will write let G be a group and H is a non-empty subset of G. So first part is that if H is a subgroup of G, then we have to show AB inverse belong to H. So first part is let H is a subgroup of G, then we have to show that AB inverse belong to H for all AB in H. Okay, so first you think since H is a subgroup, therefore H satisfying 4 properties. Okay, so you think about 4 properties and what you need means we need AB inverse. So how we will find from these conditions? So this is multiplication, means this is closure law. So first is A and second is inverse. So we will use inverse law. Okay, since H has 4 properties, means closure, associative, identity. So only we think what we prove? So we will prove AB inverse. So first we will take, since H is a subgroup, therefore by inverse axiom or inverse law, for every V belongs to H, V inverse in H. Okay. Now, since H is subgroup, therefore closure property satisfied. So also by closure law, A belong to H, B inverse belong to H, AB inverse belong to H. Okay. So first condition satisfied. So this is first condition, means here we have H is subgroup, then we have to show AB inverse belong to H. So first case satisfied. It means first part established. Okay, now converse part. So what is converse part? So here you see only we have given only one condition. So let H is a non-empty subset of G and given condition AB inverse belong to H satisfied. Okay. Then we have to show that H is a subgroup. Okay. So this is very interesting to prove, because we have only one condition and we need to show 4 conditions. Okay. So first is, so no need to write systematically like closure, associative, identity and inverse. We need to show 4 conditions as you like. There is no necessary to order. Okay. So first you see given condition, if we put B is equal to A. So if B equal to A in given condition, this is first in 1. So A inverse is equal to E belongs to H. Okay. So identity axiom satisfied. Identity law satisfied. Okay. So now we have proved identity law. So now if identity axiom satisfied, so remaining 3 conditions. Now since H is a subset of G, since H is subset of G, so each element of H are in G and G is associative. Therefore ABC equal to ABC for every ABC belong to H, means associative law satisfied. Okay. So this is second property satisfied. Now we need closure. Okay. Closure law and inverse law. So since here identity axiom satisfied, so we put, since E belong to H, therefore by given condition A is equal to E. Putting A is equal to E means E V inverse belong to H for every B in H. So E V inverse is nothing but V inverse belong to H for every B in H. So inverse axiom satisfied. Inverse law satisfied. Okay. Now we need closure. So see carefully. V belong to H implies V inverse belong to H. So in given condition, A, B inverse belong to H. Okay, implies A, B inverse B, A, B belong to H. It means closure law satisfied. Okay, so I am going to explain again for this theorem because this is very important theorem. So what is the theorem? Theorem is that a non-empty subset of H is a subgroup if it satisfying only one condition. So first part, let G be a group and H is a subgroup of G, then we need to show this condition satisfied. So since H is a subgroup, then in your mind H have four properties. Okay, so by closure law, A into B, inverse law, B inverse. So first we take A belong to H, B belong to H. So by inverse law, B inverse belong to H, and then by closure law, A into B inverse belong to H. It means first part established. Okay, now second part. What is second part? If H is a non-empty set and H satisfied given condition, then we have to show H has four conditions. Okay, so in your mind we have this condition given. So you put A equal to B. So A inverse identity. So we get identity law. Since H is a subset of G, therefore associate law satisfied always. No need anything. Now, if here, since identity element exists, so you put here E identity. So E B inverse in B inverse means for every V in H, B inverse in H. So inverse axiom satisfied. Okay, here inverse axiom satisfied. Now we need only closure law. So you have inverse. So B belong to H, B inverse belong to H. So in this place, put B is equal to B inverse means A B inverse B inverse B. So A B. This is closure. It means converse part also satisfied and hence prove the theorem.